Assistant Professor at LC Institute of Engineering and Technology. Today in Sequence and Series, I will teach you new topic, that is bounded and monotonic sequences, the sandwich theorem for sequences. So let's start. So first of all, we will see what is monotonic increasing sequence. A sequence UN is said to be monotonically increasing if UN is less than or equals to UN plus 1 for all n greater than or equals to 1. It means if you will take the value of n equals to 1, you will get U1 is less than U2 and so on. Now here is the graph of n raised to 2 plus 1 versus n. As n will move from 1 to infinite, n raised to 2 plus 1, its graph will be like this. Now you can see that this is monotonically increasing as U1 is less than U2, U2 is less than U3 and so on. So for any sequence, if you will get UN is less than or equals to UN plus 1 for all n greater than or equals to 1, then that sequence is called monotonic increasing sequence. Now we will see what is monotonic decreasing sequence. A sequence UN is called decreasing if UN is greater than or equals to UN plus 1 for all n greater than or equals to 1. If you will take the value of n equals to 1 over here, you will get U1 is greater than U2, U2 is greater than U3 and so on. So this is the graph of 1 upon n versus n. As n tends to infinite, here you can see that 1 upon n tends to 0. Here you will see that U1 is greater than U2. For n equals to 1, you will get 1 upon 1. And for n equals to 2, you will get 1 upon 2. So 1 is greater than 1 upon 2. And if you apply the same concept, you will get the graph of 1 upon n like this. And as you can see from the graph, as n tends to infinite, un, that is 1 upon n, tends to 0 and it is decreasing. So any sequence, if you will find un is greater than or equals to un plus 1 for all n greater than or equals to 1, then that is called monotonic decreasing sequence. Now this is one example. To that, the sequence 3 upon n plus 2 is decreasing. So here un is 3 upon n plus 2. So here we will find out un plus 1. To find un plus 1, we will just replace n by n plus 1. So we have un plus 1, that is equals to 3 upon n plus 1 plus 2. So this is equals to 3 upon n plus 3. So this is un plus 1. Now since n plus 2 is less than n plus 3, so 3 upon n plus 2, definitely it will be greater than 3 upon n plus 3. And 3 upon n plus 2, that is nothing but un. And 3 upon n plus 3, that is nothing but un plus 1. So we have un is greater than un plus 1 for all n greater than or equals to 1. Therefore, we can say that the sequence un is decreasing. Now we have to prove that the sequence n square upon n square plus 1 is increasing. So here un is n square upon n square plus 1. So first of all, we will find out un plus 1. To find un plus 1, we will replace n by n plus 1. So we have un plus 1 equals to, replacing n by n plus 1, so it is n plus 1 the whole square, divided by replacing n by n plus 1, so it is n plus 1 the whole square plus 1. Now here we will apply the formula of a plus b the whole square, that is a square plus 2ab plus b square. So it will become n square plus 2n plus 1 divided by n plus 1 the whole square is n square plus 2n plus 1, and this plus 1 it will become plus 2. Now this is un plus 1. Now we will find out un plus 1 minus un. So this is un plus 1 minus this is un. Now we will simplify this result. We will find out the LCM, that is n square plus 1 and n square plus 2n plus 2. Now we will multiply n square plus 2n plus 1 by n square plus 1. So we will get this result. Then after we will multiply each and every term of n square plus 2n plus 2 by n square. So we will get this result. Now we will simplify the numerator and denominator will be as it is. So after simplification we have 2n plus 1 upon n square plus 2n plus 2 into n square plus 1, and this is positive for every n greater than or equals to 1. So we have un plus 1 minus un, that is greater than 0. It means un plus 1 is greater than un for every n greater than or equals to 1. Hence we can say the sequence un is increasing sequence. Now prove that the sequence un equals to n upon n square plus 1 is decreasing sequence. Here un is n upon n square plus 1. So first of all we will find out un plus 1. So replacing n by n plus 1, that is equals to n plus 1 divided by n plus 1 the whole square plus 1, and this is equals to n plus 1 will be as it is. Now applying the formula of n plus 1 the whole square, so it will become n square plus 2n plus 1 it will become plus 2. So this is un plus 1. Now we will find out un plus 1 minus un. This is un plus 1 minus this is un. Now we will find the LCM, that is n square plus 1, n square plus 2n plus 2. So we will multiply n plus 1 by this term, that is n square plus 1, and this minus sign. Then after we multiply n square plus 2n plus 2 by n. Now we will simplify this result, and after simplification we have this result, that is minus n square minus n plus 1 in the numerator, and in the denominator we have same this term. Now for every n greater than or equals to 1, you will find that this term is negative. It means we have un plus 1 minus un is less than 0. It means we have un plus 1 is less than un for n greater than or equals to 1. Therefore the sequence un is decreasing. Now we will see what is bounded sequence. A sequence un is bounded above if there exists a number m such that un is less than or equals to m for n greater than or equals to 1. Here is the example, un equals to 5 minus n. Now if you will put down the different values of n, so for n equals to 1 it is 5 minus 1, that is 4. For n equals to 2 it is 5 minus 2 is 3. Then after for n equals to 3 it is 5 minus 3 equals to 2, and so on up to minus infinite. For n greater than or equals to 1, the values of 5 minus n will not exceed this 4. So we can say that for n greater than or equals to 1, the value of un is less than or equals to 4. So we can say that this sequence is bounded above. A sequence un is bounded below if there exists a number m such that un is greater than or equals to m for n greater than or equals to m. So for every n greater than or equals to m, if you will find out the terms un which is greater than or equals to some fixed value, say that is m, then we can say that the given sequence is bounded below. Here is the example, un equals to n. Now for different values of n, start from 1 to infinite. So we have for n equals to 1 it is 1, for 2 it is 2, and up to infinite. Now you can see that each and every term of this sequence n is 1 or greater than 1. So we can say that this sequence is a bounded below sequence. If the given sequence is bounded above and below, then the given sequence un is known as bounded sequence. Here is the example, un equals to 1 upon n. Now when n equals to 1 you will get 1, for n equals to 2 it is 1 upon 2, and as n tends to infinite, 1 upon n tends to 0. Now you can see that here un is between 0 to 1. So it is bounded above by 0 and bounded below by 1. So we can say that the given sequence un is bounded sequence. Every bounded monotonic sequence is convergent. Now show that the un whose nth term is un equals to 1 plus 1 by 3 plus 1 by 3 square and so on plus 1 upon 3 raised to n is monotonic increasing. Is it convergent? So here is the given sequence, that is un equals to 1 plus 1 upon 3 plus 1 upon 3 square and plus 1 upon 3 raised to n. Now we will find out un plus 1. So for that purpose we will replace n by n plus 1. So we have un plus 1, that is equals to 1 plus 1 upon 3 plus 1 upon 3 square plus dash 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 plus 1 upon 3 raised to n, and replacing n by n plus 1. So we have 1 upon 3 raised to n plus 1. Now we will find out un plus 1 minus un. If you subtract un from un plus 1, we have this term only, that is 1 upon 3 raised to n plus 1. And this is greater than 0 for every n greater than or equals to 1. So we have un plus 1 minus un, which is greater than 0. So we have un plus 1 that is greater than un. Therefore the sequence un is monotonic increasing. Also un equals to this sequence. Now we will find out the sum of this sequence using the sum of geometric progression, that is GP. Its formula is a into bracket 1 minus r is to n upon 1 minus r. Here a is the first term, that is 1. 1 minus r is 1 upon 3 divided by 1, so that is 1 upon 3, and it's raised to n, so it will become 1 upon 3 raised to n divided by 1 minus r, and the value of r is 1 upon 3. 3 minus 1 upon 3, that is 2 upon 3, so it is 3 upon 2, and this is 1 minus 1 upon 3 raised to n. Now this is always less than 3 by 2 for n greater than or equals to 1. Therefore we can say that un is bounded by this value, that is 3 by 2. So we can say that un is monotonic increasing and bounded above. And if the given sequence is monotonic increasing and bounded above, then it is convergent. Hence the given sequence is convergent. Now we will see Sandwich theorem. So what is Sandwich theorem? Let un, vn and wn be the three sequences such that un is less than or equals to vn, that is less than or equals to wn for all n. So if limit n tends to infinite un, that is equals to limit n tends to infinite wn, that is equals to l. Then limit n tends to vn, that is also equals to l. This is Sandwich theorem. Now we have examples related to Sandwich theorem. Discuss the convergence of sequence un equals to sin n upon n. Here un equals to sin n upon n. Now all of you know that the value of sin n is between minus 1 to 1. Dividing this inequality by n, so we have minus 1 upon n less than or equals to sin n upon n less than or equals to 1 upon n. But limit n tends to infinite minus 1 upon n, that is 0, as n tends to infinite 1 upon n tends to 0, and limit n tends to infinite 1 upon n, that is again 0, because as n tends to infinite 1 upon n tends to 0. So we have limit n tends to infinite minus 1 upon n equals to 0 and limit n tends to infinite 1 upon n equals to 0. So by Sandwich theorem we can say that limit n tends to infinite sin n upon n, that is equals to 0. Now discuss the convergence of the sequence un equals to cos square n by n. Here un equals to cos square n by n. Now all of you know that the value of cos square n is between 0 to 1. So we have 0 less than or equals to cos square n less than or equals to 1. Now dividing this inequality by n, so 0 upon n is 0, that is less than or equals to cos square n by n, and that is less than or equals to 1 upon n. But limit n tends to infinite 0, that is equals to 0, and limit n tends to infinite 1 upon n, that is equals to 0, as n tends to infinite 1 upon n tends to 0. So by sandwich theorem, we have limit n tends to infinite cos square n by n, that is equals to 0. So in today's lecture, we have discussed what is monotonic sequences, what is monotonic increasing, what is monotonic decreasing sequences, its convergence, examples related to these topics, and finally we have gone through the sandwich theorem and we have seen examples based on sandwich theorem. Thank you for watching this video. I will see you in the next lecture.